So the idea with strain is that if we have some internal normal stress right here, it can actually cause a change in the dimensions of our object, right? So if you imagine I put this thing in tension, it could actually probably lengthen a little bit. And so our definition for strain is if our change in the dimension, we're just going to look at the axial case right now. So for our change in dimension, we call this delta, and our original length is L. Then the definition of the strain, we use epsilon, is it's equal to delta divided by L, and this is the average strain across the whole bar. And then if you want to get the strain at some point, all you have to do is just take like the limit as your delta L goes as your delta L goes to 0 of basically some small slice of delta related to some small slice of length, which just becomes d delta over dl. But really this is like the main form you're going to see it in, because again, most of these we're assuming have like constant properties and things like that, right? And so the units, if you think about this, our delta is going to be in terms of length, and our L is also going to be in terms of length. So these are actually unitless quantities, but what they usually end up being reported in is either radians, which is also unitless, so it's kind of weird, but radians or microradians. So we do a micro radian like that. You'll also see it written as just like micro epsilon for some reason. I don't know. The units are kind of weird, but it's technically unitless. Sometimes you'll throw a micro on here just because when we're talking about like metal beams and stuff, the amount that it displaces, the delta, is really small compared to like the original length, right? And so now we can talk about the shear strain, since that was the normal strain. So the shear strain, if we have a shearing of our object, right? If you imagine if I take my square originally right here and then I shear it, I'm going to have my original length, and then my delta is going to be perpendicular in the shear direction, right? So my average shear, we use gamma. The average shear is going to just equal, again, delta, and I guess we'll just say delta x over our L, and then, you know, you could take the limit with this, right? So your delta, I guess if this is average, would just be a limit as delta L goes to 0 of our differential, or I guess our delta over this. There's a capital and lowercase delta here, so it's kind of weird to say this out loud, but we have a d delta x over dl. But again, this average case is what I'd recommend thinking about. However, with the shear strain, because we're talking about such small angles, what we usually do is we say, okay, this angle right here, I mean such small strains, this angle right here is going to be pretty small, right? Now I know that the tangent to theta is opposite over adjacent, so this equals my delta x over L, which, hey, is our strain. But with the small angle approximation, we can say that theta is approximately equal to tangent of theta, and therefore our shear strain, you'll sometimes see it as basically just our change in angle. So it's just equal to this theta right here, or sometimes they'll put this right here, they'll call this like theta prime, and then they'll see it's equal to like pi over 2 minus theta prime, because shear strain basically measures how the shape of it changes with respect to some axes. So if you imagine in the original shape, I have like some perpendicular components right here, and then I shear it, these axes are going to transform into something that might look more like this. So measuring the angle between these originally perpendicular axes is how shear strain is like technically defined. And then the third type of strain that we have is something called thermal strain. So basically when something heats up, it can usually get bigger, and what we say is that it's approximately proportional to the amount of temperature change. So if I have my epsilon, thermal is going to equal some proportionality delta, or this is an alpha, sorry, times the change in temperature. So basically, for each unit of temperature change, I'm getting a proportional unit of strain. And then if I want to get the total strain acting in some direction, I just add up the strain from my stress plus the strain from thermal. So if I have a T1 to T2 right here, this would just be alpha, which is usually going to be given, times our T2 minus our T1. And the thing about thermal strain is that these all had directions, right? So like our shear strain is in the shear direction. Our normal strain makes it either elongate or compress. And our thermal strain, however, is going to act in all directions. If we're talking about like an isotropic material, the strain is going to be the same in every direction. Now, when you have some material, what you're going to do is usually something called a tension test. There's a bunch of data about different materials like steel or whatever you happen to be using, aluminum. Or basically what they do is they take a little slice of it and then they hook it up to these clamps, right? They'll like grab it like this kind of basically. And then what they do is they just increase the force more and more slowly until this thing fractures. And then what we get is a diagram of the strain and the stress. So the stress applied is inferred based on how much force is being applied and the area. So you actually have here is called the engineering stress strain diagram. So you see it does some weird stuff right here. This dotted line shows what's actually happening. And then this line is for the engineering stress, because basically what you're seeing right here is that material's getting thinner and thinner. It's called necking, or right when it's about to fail. Basically, it starts looking like this, which means that it can't support as much of a load because its area is reduced, which means that the stress is going to increase. So even though the stress basically increases until it fails, it looks like the stress actually dips down with respect to the area. If we just measure the original area, because that's how these things work, we get the original area and we just compare that to the force that we're applying. So starting at the beginning here, basically what we have is the more stress we apply, the more strain we get. So basically it's getting longer and longer and longer as we apply more and more of a load until eventually we hit this point right here. This is called the proportional limit. So at this point, sigma and epsilon are no longer proportional. What you're going to get is something called yielding, where basically you're getting much more lengthening for your stress. It can even kind of go down, and then basically you're just going to get a bunch of lengthening as this material kind of stretches out with minimal change in how much load, how much stress you're applying. And then eventually you hit a point where the stress that you need to apply increases and increases as the strain gets longer and longer and longer, until eventually you hit to this point right here, which we talk about is called necking. And then eventually you hit a point right here where it fractures. And this is what it's like for something called a ductile material, which means that it can lengthen a lot as you pull on it before it fails, right? It goes pretty far. It's got all the strain before it fails. You also have things called brittle materials, which their diagram would just look something like this. Boop, right there, it fails. So basically you get like this linear region, more and more and more, and then it just breaks. There's no yielding. It doesn't like lengthen. It's kind of like the difference between like a hard taffy or like a taffy if you like heat it up, right, and you can bend it a little bit. Now this orange line right here is something called strain hardening. So the idea is that if I take my material and I load it all the way into this region right here, and then I unload it, it's going to basically go all the way down to zero stress in a line that's parallel to this linear region right here. So if I take something and I add this load all the way up to here, and then I release the load, I'll actually get a stronger material that can be in the linear region for longer, which is usually the region right before we say it fails. Like if you remember earlier, we were talking about the yielding stress is kind of like the condition for when it failed. So now the yielding stress would be up here. It would technically be closer to like the ultimate fracture or fail, but it is useful in a lot of cases. And sometimes manufacturing processes will take this into account. So if you have things like cold rolled steel, where they'll actually bring it into the strain hardening region in order to get a stronger material. Now, in order to find what stress we call yielding, it's a little bit ambiguous because it kind of just gets more and more like longer. It has more strain once we apply this load right here. But there is a technique. It's called the 2% offset technique. So basically, the strain is 2% right here. We go over to our 2%, and then we imagine loading it all the way up to here. So basically, I should be more clear. This offset right here is 2%. Percent doesn't have units, so this would be the same thing as, right, 0.02. And then I guess if you really wanted to throw units on here for strain, you could put like a radians or whatever, right? And then we take a line that's parallel to this one, and we go all the way up to here. And we say this right here is the stress and strain that we'd have to load it up to, so that when it's unloaded, it has a 2% strain relative to the original case. So in the linear region right here, we're assuming basically that it obeys Hooke's law. So like the lengthening or the strain relative to the length is proportional to the amount of internal stress we give it. So there's something called E. It's called Young's modulus, or the modulus of elasticity. And it's basically equal to the ratio of how much stress we get per amount of strain. So basically it's just like the slope of this right here. So the higher the slope, the more stress you can apply for a certain amount of strain, right? Which means that a higher E value basically means that you have a stronger material. And then you also have something called G, which is the modulus of rigidity. And this is the same thing, but basically for shear stress. So we have the shear stress divided by the shear strain. And then there's one other ratio that we can talk about, and that's something called Poisson's ratio. It's the Greek letter nu, which is negative E lateral over, that's not an E, it's an epsilon technically. And then we have axial right here. So the idea with that is if you imagine intuitively, like if I go ahead and I take this bar, right? I got a bar, all right, and I put a load on it. I put a force. That's not what I want for a force. So I put a force on here. What's going to happen is it's going to lengthen, right? But because of conservation of volume, it's also going to get a little bit thinner. So we're actually going to get something that looks something like this, right? So there's going to be a delta, a change in length, which would be this length right here, plus this length right here, in the axial or the longitudinal direction. But there's also going to be a delta, which would be this length right here, plus this length right here, in the lateral direction or the perpendicular to the axial direction. So the sign convention here is that if our delta is negative, it means that it's gotten smaller, which is where this negative sign comes out here. So you can imagine that if basically I pull this material, I make it longer, I'm going to have a positive axial strain, and that's going to give me a negative axial strain if I'm stretching it out, and then it's getting thinner here, which is going to be a positive Poisson's ratio. In some cases, you can get stuff like negative Poisson's ratio because of weird materials that we've made, like foams that expand when you pull on them. But for the most part, Poisson's ratio is going to be between like 0 and 0.5. It would be 0 for something like cork, where you can basically just compress it and it won't get bigger or wider or like thinner. And then for something that's very elastic like rubber, you're going to get pretty close to 0.5, which comes from the conservation of volume, which technically isn't a thing, right? I could pack something in so that it has more density, but if you assume conservation of volume, the maximum Poisson's ratio would technically be 0.5. And then the relationship between all of these values, just to kind of give you an equation real quick, is that G has to equal E all over 2 times 1 minus Poisson's ratio. So if you ever need to convert between one of these, if you know two of them and you want to get the other, this is how you do it. Now, another concept that they kind of just sprinkle on here is something called Saint-Venant's principle. So the idea, I think the best way to explain this is that localized effects disappear at a certain distance away from them. So you can see right here, if I have a force right here, it's going to basically, our material is going to like be pulled a little bit more closer to this effect, right? So we're going to have this kind of warping in the material. But the principle says that once we get far enough away, these grid lines look pretty much like a grid, like they're perpendicular, right? And so more technically, what we would say is that the longest dimension in the lateral, so if we imagine we had like some thickness here, right? Whatever is higher, either the thickness or the width, which would be the width in this case, if we take the width and we go that far away from where the load is applied, so like it would be probably right around here, any localized effects from the force should basically kind of disappear. And so this is the main idea with strain, is we're assuming it's just kind of averaging out, right? The localized effects of where we happen to apply it aren't actually going to affect the outcome on average, like the average strain. So let's take a look at an example right here. I've got an original beam and then a beam after stretching out, and the question I want to ask is, where is this point B going to end up when all of this is done? So the first thing I can do is I can find the strain in the beam. If we're assuming that this is all the same material, it's under the same loading, then the strain is going to be the same on average throughout this entire beam, right? So we can go ahead and do, say that epsilon has to equal our delta over our length, and let's just count this out. This would be 3, 6, 8, so our length here is 8, and then our delta is 1, 2, 3, 4. It's getting 4 longer, so it would just be 1/2, all right? Now what we can say, because the strain is the same, is that our delta has to equal, right, like our strain times our length, which means that the delta between A and B has to equal the strain, which should be the same, so it's just 1/2, times the length between here and here, which we can see originally is 3, so this equals 3/2. So our delta between AB is going to be the additional length, right? So originally between A and B, we had a length of 3, so we're still going to have this length of 1, 2, 3, but then we're also going to have a delta of 3/2. So if we go 3, we're also going to have to add over 1.5, which means that the new location of B is going to be right here. And we could have also gotten that from the distance between B and C. Now, one thing that's really useful when you're analyzing different setups is the concept of superposition. So the idea here is that we can look at the case of different individual loadings and then combine together their effects. So basically, if you imagine like I had a beam, right, and it had like different loads applied at different points, what I could do is I can look in the sections of each of these, right? So if I have like force here, right, I don't really know. These would have to balance out, right? But basically, even if these are different materials and they're under different loadings, I could find the delta in this region, add the delta in this region, and add the delta in this region, and all of those would combine to give me the total delta of this thing under this applied loading. So if you recall, the modulus of elasticity is basically just the ratio between stress and strain, and this is going to be basically a constant for whatever material we're looking at. Now remember that our stress is just the force over area, so we're just going to call this P over A, and then we'll also have our epsilon right here. Now if I solve for epsilon, I get that my epsilon has to equal P over AE, but remember that epsilon is just equal to delta over L. So if I multiply over the L, what I get from all this is that my delta has to equal PL over AE. So my loading is going to be known, the original length, the area. This is just property of the material. Now if I add this up for each of my individual sections, which might have different length, a different area, cross-sectional area, and a different E, what I'll get is the total displacement for that entire thing. And then if you want to do it with calculus because you have like P or A or something as a function of X, then you just want to integrate from 0 to your length. P is a function of X over A is a function of X. Hopefully E isn't a function of X, but I guess if it is, you can put E as a function of X dx. Now this other example that I wanted to show, we have our beam right here, but you can see that it's fixed at both ends and it has a load applied right here. So if I did a free body diagram, I would have my load right here, right? I'd have my P. I'd also have reactions in the Y, in the X, and moments, but let's just look at the forces in the X right now. Because the forces in the Y, if I don't have any applied loads, there probably isn't going to be a reaction in the Y, right? So anyway, we'll just have an AX here, and then also, I don't know why I call this AX, we'll just call this RA, actually AX is fine. And then we'll have a BX reaction right here. And let's just say that the problem's asking for just like the reactions in the X direction, right? Because we know that this load right here is going to cause some weird thing where the AX is going to be something and the BX is going to be something. And just based on statics, all we could do is basically just sum the forces in the X. We may be able to get away with summing the moments. But in this case right here, all of these are collinear, so that's not even going to help us. Really, we're stuck with one equation unless we start using these ideas that we've developed here. So what you could do is you could say, okay, I'm going to analyze this as just a beam with this load P right here, right? So I have my beam going all the way through right here. It's a pretty terrible beam, but I think you get the idea. We'd have our AX, we'd have our P, and I noticed that this section of the beam, if I made like a cut right here and just looked at this side, it doesn't have any internal force, which means it isn't going to have a delta. So our delta would just be the internal force in this region right here. So whatever P that is, times our length, which is, I don't know, a length would have to be given in this case, divided by A, which is the cross-sectional area, times E, which would probably be given if you know what the material is. And then what we would do is we would add the case where we have just this BX right here, right? So my delta, when I just have this BX, which is going to go through the whole beam in this case, right? Because I'm going to have my AX, and then I'm also going to have my BX right here, BX, so I'm going to have an internal force in here, PL over AE. Those two added together, if I'm taking a look at just like this setup right here, it's fixed at both ends, which means that the lengthening and the contractions in this beam all have to cancel out, right? So my delta from this case plus my delta from this case would have to equal 0, and that would give me another equation which I could use to simplify this problem. And now one last example I want to leave you with, just so you can start thinking about the kinds of problems they can ask and how you can approach them with like, what do you know and what don't you know and what equations can you use, is this one right here. So in this case, we actually have two materials, and we're told that they're like welded or glued together basically. So we have our inner material right here, and we have our outer material. We're applying some force, and we want to know like how much it's going to compress, right? So if they're welded, if they're glued, if they're stuck together, then basically what's going to happen, right? If I think in like a 2D case, is I'm going to have my outer right here, and I'm going to have my inner part right here, and then I'm going to basically compress it, right? So it's going to get smaller, maybe it'll get wider, okay? It's going to look like this. But if it's glued together, then I'm going to assume that the heights of these are going to be the same, which means that the delta of, I don't know, we'll just call this like the inner, has to equal the delta of the outer right here. And then I can also say this force right here has to be felt between this blue material and this internal material right here, right? So this P, I know it looks like, or this F, is just going onto this white, but really what you're probably going to have is something like, if this is our material, we're going to have some plate that's kind of distributing the force across the entire thing. So there could be some component of this force that we're subjecting to this assembly in the blue and here, but we know those have to add up to our F, right? Another way you can think about this is that if I look at my reactions down here, I'm going to reaction from the blue, so reaction from the ground or whatever's supporting it, right? In the blue and in the white. So what I can say is that these two have to be equal and opposite, so I can say that my F has to equal, right, the force reaction, we'll just do inner and outer because that's what I had earlier, plus force reaction outer. And there's all sorts of stuff that you could ask, but this kind of gives you an idea of how you want to think about these problems. It's really about what do I know and what can I use to simplify these setups based on like what lengths, what do I know, what lengths have to be the same, what deformations have to be equal to 0 or equal to like a certain amount that I might know, right? And I could have also added in thermal here. I know we didn't have any thermal examples, but like they could have also given you the change in temperature, and then whatever strain you got from just the mechanical of the forces, you just have to add on that alpha times delta T that we talked about earlier. Where was it? It was like right up. Oh, yeah, right here. You would just add up your normal stress and your T. And so yeah, that's about it for a strain, and I'll see you later.